Good afternoon, class. We are looking at statistics practice test number 5, module 5, covering chapters 10, 11, and 12. Here's chapter 11, goodness of fit and contingency table. Could somebody read the question, please?
Goodness of fit test in multinomial experiments. Here are the observed frequencies from 4 categories, 5, 6, 8, and 13. At 0.05 significance level, test the claim that the 4 categories are all equally likely. A, state the null and alternative hypothesis. B, what is the expected frequency for each of the 4 categories? C, what is the value of the test statistic? D, find the critical values. E, make a decision.
Perfect. So definition of a goodness of fit. Could somebody read that, please? Go ahead, please.
A goodness of fit test is used to test the hypothesis that an observed frequency distribution fits or conforms to some claimed distribution. Goodness of fit hypothesis tests are always right-tailed. If the sum of these weighted square deviations
Chi-squared equals summation of O minus E observed minus expected quantity squared over E. Continue, please.
Is small, the observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from that distribution. Only when the sum is large is the reason to question the distribution. Therefore, the chi-square goodness of fit test is always a right-tail test.
Excellent. Well, when we have an equally likely, then the expected value is the total number of observations over the number of categories. Otherwise, E is equal to N times P if they have different weights, different proportions, different percentages. So E is N over K. In this case, N would be 5 plus 6 plus 8 plus 13. The summation of O, here's the values we have experienced, we have observed. We are going to add them up, and there are 4 categories. We divide by 4. So the idea is that the expected value for each one is actually 8 if they are equally likely. In other words, when we look at this concept of a multinomial, just think about binomials have 2 outcomes. Multinomials have more than 2. In this case, there are 4 outcomes. So each one must have an equal chance of 1/4 when they say equally likely. And by the way, they don't have to. They may add different percentages, but they must add up to 1. So when they are equally likely, 1/4 or 0.25 or 25% each. A given multinomial experiment with K equals 4, 1, 2, 3, 4 categories. Alpha is 0.05. We use a goodness of fit test. Each expected frequency is 8, which satisfies the requirement of being a value of at least 5. If expected count is less than 5, the result of chi-square test will not be accurate. So what are these? These are the same steps that we do with the test of hypothesis. Okay. So we are going to go through the process. Same question. We are going to write the 4 steps. Number 1, H0. P1 is equal to P2 equals P3 equals P4 because these are different proportions. And since there are 4 of them, we stop at 4. And since they are equal, you might say equal to 0.25. It has the same meaning. H1 at least one of the probabilities is different from the others. And it makes it a right tail test. We are again looking at the limitation of chi-square. That's why we make it a right tail test. I will discuss it even if you assume it's two tail test. Now, the formula chi-square is summation of O minus E quantities squared over E, and degrees of freedom is K minus 1. So obviously degrees of freedom in this case is obviously is 3. But what is observed minus E? We have decided that it is supposed to have an observed value of 8. We calculated it from before. So now each value, 5 minus 8, quantity squared divided by 8, plus 6 minus 8 quantity squared divided by 8, plus 8 minus 8 quantity squared divided by 2, all the way to the last one. And of course, you can make up 4 fractions or just one fraction with the denominator 8. You do the evaluation, you end up with 4.750. Critical value is fairly simple. Alpha is 0.05. Degrees of freedom is 1, 2, 3, 4 minus 1 or 3. And now chi-square distribution. On the left column, you look up the degrees of freedom, which is 3. And at the top, you want the 0.05. Remember, you need the area to the right, and that gives us this value, 7.815. So the chi-squared value is 7.815, known as the critical value. If we do the drawing, here's the critical value, 7.815 from the table or technology. Here's the test statistic way into the non-rejection region. Non-rejection region. Therefore, we are not rejecting H0, or we fail to reject H0. So if you're not rejecting H0, you're not rejecting the claim becomes true. So that's why it's important to know which one represents your claim, H0 or H1. So do not reject H0, the claim is true. There is sufficient evidence to support the claim that the 4 categories are all equally likely. Now, even if we went with a two-tail test, again, because of the limitation of the table and everything, we go with the one-tail test. But even if we did, now this 0.05 gets divided by 2. And for this one, this becomes 0.05 divided by 2, or 0.025. And for the other one, if you have 2, for a two-tail test, you get those chi-squared values. One of them is 0.216, one of them is 9.348, and test statistic 4.750 is still in between, and you have the same result, which is fail to reject H0. Again, you don't have to do this by hand, so I'm going to quickly show you. It's important to understand the concept. And again, this is an online calculator. If you go with TI, you are going to clear list L1 and L2, and you go with stat test, chi-squared, GOF, goodness of it. GOF stands for the goodness of it, L1 and L2. In L1, you put the observed values, the ones that have been given to us, and L2 is the expected value. It's happened to be 8 for all of them. So here's L1, here's L2. So chi-squared GOF, put the suffix. Observed is in L1, expected is in L2, degrees of freedom is 3, calculate. Notice the numbers. Here's one of them. This is the test statistic that we had calculated on our own. This is the p-value. The p-value is the area to the right of test statistics. So this would be the p-value. So p-value is 0.1910 and continues indefinitely, which is way larger than alpha of 0.05. Don't reject H0. So we get to the same result. Okay, same result. Could somebody read this question, please? Go ahead, please.
Goodness of fit test and multinomial experiments. A professor asked 40 of his students to identify the tire they would select as a flat tire of a car carrying 4 students who missed a test, an excuse. The following table summarizes the result. Use a 0.05 significance level to test the claim that all 4 tires have equal proportions of being claimed as flat.
All right, so these are the observed values that have been given. And again, they are equally likely. So E is N over K, add them up, divide by 4, and that makes it 10. So each value is larger than 5, so we can do the goodness of fit. And let capital L represent the left, capital R the rear, lowercase r right, capital F front. And so when we write this, instead of spelling it out, so probability or for proportion of LF, that means left front. RF, that means right front, so on and so forth. There are 4 of them, they're all the same, and they're all 0.25. H1, at least one of the proportions is not equal to 0.25. It's a two-tailed test. However, remember, with the limitation, we go with the right tail test. Let's calculate the observed value. Again, you don't have to do this by hand, but we have only 4 categories. It can be easily done by hand. So following this formula, so 11 minus 10 squared, 15 minus 10 squared, 8 minus 10 squared, 6 minus 10 squared, add them up, divided by the expected value, which is 10, and we get 4.6. We get the same critical value as before because alpha is the same, 0.05. Degrees of freedom of k minus 1, 1, 2, 3, 4 minus 1 is 3. So we get the same answer. And when we go with the graph, clearly the test statistic is way into the non-rejection region. The tail starts from 7.815 and it goes to infinity. This is in a non-rejection region. You fail to reject or you don't reject H0, that means you don't reject the claim. The claim is true. So don't reject H0, the claim is true. There is sufficient evidence to support the claim that all 4 tires have equal proportions of being claimed as flat. And if we were to deal with the two-tailed test, I hope you see that this number, the test statistic, is also in between. I don't even have to do the drawing, so it becomes clear that in that sense, it gives us the same answer. Again, in reality, it's two-tailed test, but right-tailed test will work. And so what it means when 4 students identify the flat tires, it is not likely for all to select the same tire if it's an excuse. Test of independence. Using a 0.05 significance level, test the claim that when the Titanic sank, whether someone survived or died is independent of whether that person is a man, woman, boy, or girl. So let's discuss this concept. First, this table is given and we're going to put the total. We add these two, these two, these two. So we make up the total for the 4 columns. We make up the total for the 2 rows. And this one is the grand total. If you add up this row or this column, they must give you the same answer. Now we use the formula. The expected value is defined as the row sum times the column sum over the grand total. So I want to use this for the upper left hand cell. So we want to use that as an example for this one. These are all observed values. So I want to show you by hand how it's done. Needless to say, again, you don't have to do it by hand. So if the observed value is 332, what is the expected value? According to this formula, what is the row sum? This number times column sum. So this one belongs to this row, belongs to this column, this product of these two, divided by the grand total of 22, 23. Take a look. Again, we are interested in finding the expected value for this. Here's the total for the row. Here's the total for the column. Multiply, divided by the grand total. That's what we have. Now, if we continue with the same procedure for each entry, so it takes a little bit of a time. That's why you don't do it by hand. It gives you this, which means, for example, for 332, we did the calculation. For the other ones, we're going to go with those calculations. Those are all expected values. For example, for this, the expected value is this number. For this one, the expected value is this number. More importantly, what is the meaning of that? Somebody read the interpretation. So we want to do the interpretation of, for example, this cell, which has the observed value of 332. That's what actually happened. This would be the expected. Somebody read that, please.
To interpret this result for this upper left-hand cell, although O equals 332 men survived, we would have expected frequency equals 537.36 men to survive. The survivability is independent of whether the person is a man, woman, boy, or girl. There is a discrepancy between O equals 332 and expected frequency equals 537.36, and such discrepancies are key components of the test statistic that is a collective measure of the overall disagreement between the observed frequencies and the frequencies expected with independence between the row and column variables.
Perfect. Please continue.
To interpret this result for the lower left-hand cell, we can say that although O equals 1,360 men actually died, we would have expected frequency equals 1,154.64 men to die. Survivability is independent of whether the person is a man, woman, boy, or girl.
Perfect. So in other words, if they are independent, this is the observed value, but the expected value says this is the case. For this one, this is the observed value, but this is the expectation. For this one, this is the observed value, but this is the expectation. And of course, what you want to notice is that the summation of E in rows and columns are consistent. For example, if you look at this one, whether we add these two numbers, we get this, or if we add the E, the expected values, this number and this number gives us this, or if you go with the row, if you add up 332, 318, 29, 27, you get this. If you add up these numbers, also you get 706. Only difference may be due to round off error, but if you add them up, you should get the same answer. All right. Contingency table. A contingency table or two-way frequency table is a table consisting of frequency count of categorical data corresponding to two different variables. One variable is used to categorize rows, and a second variable is used to categorize columns. Could somebody read it, please?
When data can be tabulated in table form in terms of frequencies, several types of hypotheses can be tested by using the chi-square test. Test of independence of variables. In a test of independence, we test the null hypothesis that in a contingency table, the row and column variables are independent. That is, there is no dependency between the row variable and the column variable. The test of independence of variables is used to determine whether two variables are independent of or related to each other when a single sample is selected.
Please continue.
Tests of independence are always right-tailed. If the sum of these weighted square deviations
Summation of O minus E quantity squared over E
is small, the observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from the distribution. Only when the sum is large is the reason to question the distribution. Therefore, the test of independence is always a right-tailed test.
Excellent. So in essence, it uses the same procedure as a multinomial when it comes to calculating the test statistic. So I'm going to continue with the question that we had in hand. So we want to do the test of independence. And the way the test of independence work, the requirements are, we're going to assume randomness, and results are frequency counts, and the expected values must be large. How large is large? Larger than 5, and obviously they are all larger than 5. So here's H0. Whether a person survived is independent of whether the person is a man, woman, or boy, or a girl. Or you might say the row variable is independent of the column variable. And that is the claim that we are looking at. H1 or HA, surviving the Titanic and being a man, woman, boy, or girl is dependent. Instead of independent, we can say dependent. Or the row variable is dependent or related to the column variable, and it's a right-tail test. So this is one general form of writing anything, by the way. So the test statistic is just like before. Degrees of freedom is R minus 1 times C minus 1. R represents the number of rows. C represents the number of columns. So for the sake of argument here, we have 1, 2, 3, 4 columns and 2 rows. So 2 minus 1 times 4 minus 1 makes it 3. So you see how the degrees of freedom works. The second step is to calculate test statistic. O minus E squared over E. So for example, for the first one, 332 minus 537.36 B squared and divided by the expected value. So this is O, this is E. The second one would be 308 plus 318 minus 134.022 squared divided by 134.022. You do the same thing here, 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 here. And the last one, plus 18 minus 30.709 quantity squared divided by the expected value 30.709. Again, You don't have to do it by hand. I just wanted to show you how it's done in case. And we end up with a test statistic, which is huge, 507.084. As far as the degrees of freedom is concerned and the choice of alpha, it's just degrees of freedom, as I mentioned it before, the number of rows -1, the number of columns -1, the product is 3, alpha is 0.05 from the table or technology, we get 7.815. And when we do the drawing, this is way into the rejection region. It's way larger than the critical value. So clearly reject H0. So if you're rejecting H0, you're rejecting claim, and that means they are not independent. The row variables and column variables are not. And so here's how we write it. Reject H0, the claim is false. There is not sufficient evidence to support the claim that when the Titanic sank, whether someone survived or died is independent of whether the person is a man, woman, boy, or girl. Survival and gender are dependent. That's one short way of writing. Now, of course, it can be done with technology as follows. We go with a matrix, and to access matrix in a TI, second and press x to the power of -1, edit. First you enter the dimension, and then we go with the chi-square test, and the observed matrix must be A. So take a look at what we do. Matrix A, and we make it 2 by 4, and we put these numbers 332, 318, 29, 27 here. And the second row, 1360, 104, 35, and that doesn't show the last entry. So all you have to do, plug in matrix A. Now, we go to tests, we go to chi-square test, see what it does. It tells you the observed is A, the expected is B. You don't have to do anything, just follow that and click on calculate. And when it calculates, you can also look up the B matrix. The B matrix automatically gives you the expected frequency, of course, with a lot more decimals. So you don't have to calculate the expected one, it does it for you. But here's what I want you to notice. First and foremost, look at the number. We had calculated it by hand, very close to the one done by calculator. And the p-value is 0. Clearly, the area to the right of this number is almost 0, which is less than alpha 0.05 reject H0. So the p-value, okay, of course, if you go with the table class, you get way less than 0.005. But the area to the right of the, if you assume this is the number and it's not, so this area, okay, which is almost nothing. And so the p-value is 0, which is less than alpha, which was 0.05. So same result, reject H0. To test up homogeneity using the following table with a 0.05 significant level, test the effect of poster gender on survey response by men. Ultimately, it becomes the same as the chi-square test, okay? And so men, women, and these are the gender of interviewers, and men who agree, men who disagree, and so forth. In other words, depending upon who is doing the interviewing, we may have a different answer. So, could somebody read this, please? Go ahead, please.
Chi-square test of homogeneity. Test of homogeneity of proportions is a test of the claim that different populations have the same proportions of some characteristics. The test of homogeneity of proportions is used to determine whether the proportions for a variable are equal when several samples are selected from different populations. Tests of homogeneity are right-tailed. If the sum of these weighted square deviations
Summation of O minus E quantity squared over E
is small, the observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from that distribution. Only when the sum is large is the reason to question the distribution. Therefore, test of homogeneity is always a right-tailed test.
Excellent. So again, similar to what we have done, the concept is that in the case of test of homogeneity, we have several samples, but conceptually they work exactly the same as what we did in the case of a test of independence. So the very first thing, we add them up. 560 and 240, 308 and 92. And we are going to go with the row. We add up these two numbers, we add up these two numbers, and this is the grand total again. And so we can find the expected value just as before, row sum times column sum over the grand total. So here's the table of expected value. Again, as an example, for number 560, how did we get 578.67? Well, for number 560, the row sum is 868. For number 560, the column sum is 800. So the product of these two times the grand sum of 1200 divided by the grand sum of 1200. And that's how we get this one, meaning we can easily find the rest. So it's very simple, class. Requirement check. Based on the description of this study, we will treat the subject as being randomly selected and randomly assigned to the different posters. The results are expressed as frequency counts. The expected frequencies are all at least 5. If so, the count will be approximately normally distributed. So we're going to work on this. This is the formula we're going to use. Again, degrees of freedom, row minus 1 times column minus 1. And this is what has been calculated. And we have the table in case we want to look things up. And of course, you can do it by technology. So H0, the proportion of agree-disagree responses are the same for subjects interviewed by men and the subjects interviewed by women. In other words, P1 equals P2 equals P3. There were 4 of them, but if there are even 10 of them, you say you go all the way to P sub n. Or you might say survey response by men are independent of pollster gender. And that is the claim. H1, the proportions are different, or at least one proportion is different from the others, or survey responses by men depend on pollster gender. So there are various ways of writing them. I've shown you 3 different ways, so you want to write them accordingly. And that makes it a right-tail test. So let's go with the formula for the test statistic. And so 560 minus 578.67 quantity squared divided by that, the same thing here, the same thing here, the same thing here. So the last one would be 92 minus 110.67 quantity squared over 110.67. And that gives us the following number, 6.529. The critical value, as you see, there are 2 rows, 2 columns, 2 minus 1 times 2 minus 1 is 1, alpha is 0.05. So degrees of freedom is 1. So you look for 1. And this one, 0.05, it's the area to the right. And there you have a 3.841. And all we have to do the drawing and look at the location of test statistic. So when we do the drawing, the critical value of 3.841 here, here's the tape, and the test statistic is way into the rejection region, rejection region. Therefore, reject H0. That means reject the claim. That means the claim is false. So we write reject H0, reject independence in essence. The claim is false. There is not sufficient evidence to support the claim that the proportion of agree-disagree responses are the same for the subjects interviewed by men and the subjects interviewed by women. And that would be done. But a second method of writing the same thing. There is sufficient evidence to reject the claim of equal proportions. That is done. Again, a third way of writing the same thing. Survey responses by men depend on poster gender. And we're done. If you were to treat this as a two-tailed test, then the numbers that we get for chi-squared, one of them is this number, 0.001, almost zero, and one of them is this. And this is way larger than this. And again, it puts it into the rejection region, resulting in the same answer. Last question, somebody read that, please.
Test of homogeneity. Using the following table with a 0.05 significance level, test the association between people living in a city and becoming infected with a highly resistant bacteria.
Perfect. So we have a bacterial condition that people are either infected or not. We have a living location, which is either city or outside. So again, you can put it into, Excel file. You can put it into TI. You can put it in some sort of a technology and do the math online. But first, let's start with the first step. H0, whether a person is infected, is independent of whether the person lives in the city or outside the city. Or P1 equals P2, P3, all the way to P7. That would be the claim. Whether a person is infected is dependent of whether the person lives in the city or outside the city. That we are going to go with the right tail test. So here's the formula, and we are going to go with that. We have to calculate the expected values. And to find the expected values, here's the sum here, here's the sum here, here's the sum, and here's the sum, and here's the grand total. So for example, for this number, we're going to multiply the row sum, which is 10,162, times the column sum, which is 17,139, and we're going to divide it by the grand total of 42,048. So 4239 is the observed value. The expected is 4142.088. And this is actually, if you go with, and you put the formula in Excel, it goes very fast. So you put this one in Excel and then put the formula for one cell and then repeat it for the rest of them. It does that. You can also expect them to calculate this for you. Observe minus E quantity squared over E. So it calculates it for each cell. And if you add them up, that would be the answer here. Or say this number, 4,142.088 minus 4239, or vice versa. It doesn't matter which one, because you're going to square that, it doesn't matter. But it is important to divide by the expected value. And you go all the way to the last one, this number minus this number, and square that, divided by the expected value. And we end up, or as I mentioned, if you go with the simple process of putting the formula into Excel, it will calculate the number for test statistic, which becomes 5.04 7.424. As far as the degrees of freedom, just like the previous one, 2 minus 1 times 2 minus 1, because we have 2 rows and 2 columns. Degrees of freedom is 1, alpha is 0.05. We have the same value, namely 3.841. This is 3.841. So if we do the drawing, this is 3.841. This is your critical value. Test statistic is way into the rejection region. So you reject H0. Now, if you go with the technology, degrees of freedom is 1, alpha is 0.05. Here's the chi-square test. Here's the p-value. And by the way, speaking of the p-value, if I were to show you, would be this area. Area to the right of test statistic is the p-value. This is the p-value. Area to the right of test statistic. And so the p-value, of course, if you want to go with that route, is less than alpha of 0.05, and we have the same result. Reject H0. And therefore, you're rejecting independence and the claim. So this is also from technology. Everything from technology is here, the test statistic, the critical value, and the p-value. And here's the decision, reject H0, that means reject independence. The claim is false. There's not sufficient evidence to support the claim that whether a person is infected is independent of whether the person lives in the city or outside the city. Another way of putting it, whether a person is infected is dependent of whether the person lives in the city or outside the city.